Hello and welcome to this Chapter 5 demo of solutions. Hopefully, after you've watched this, you'll have a better understanding of what the book is asking for in terms of what kind of probabilities it wants and how to do those calculations. So for the first demo, I'd like to do problem number 3 out of the back of the Chapter 5. And it goes on, it says, suppose that for a recent admission class, an Ivy League college received 2,851 applications for admission. Okay, so your grand total, so I've typed in the grand total here, and then we've got, of this group, it admitted 1,033 early, rejected outright 854, and deferred 964 to the regular admissions for further consideration. In the past, the school admitted 18% of the deferred early admission applicants during regular admission process. Counting the students admitted early and the students admitted during regular admission process, the total class size was 2,375. So it says let E, R, and D represent the events that the student who applies for early admission is admitted, rejected outright, that would be the R, and deferred to the regular admission pool. So we need to use the data to estimate probability of E, probability of R, probability of D. So just to check the totals here, I did a sum of C3, so that's this. So the probability of E is going to be this value early divided by the total. So all you're going to do is you're going to say equals this divided by this, and it's going to be the same for each one. So I press F4 to get the absolute. And so the answer is 0.3623 or 36.23%. Copy that down, and I get the probability of R rejected and then the probability of deferred. For part B, it says, are the events E and D mutually exclusive? The answer here for part B is yes, they're mutually exclusive, and you get that by thinking about it in terms of, well, if you're admitted early, could you be deferred? And the answer is no, you couldn't. And so that means they are mutually exclusive. Yes. That also means that the probability of E intersection D is 0. For part C, it says, for the 2,375 students who were admitted, what is the probability that a randomly selected student was accepted during early admission? So for early admission, we had 1,033, and we will use this number. That's the ones that were admitted. So the probability then is this number divided by this number. So the probability is 43.49%. And I'm not sure I was recording here, but we have the 1,033 here and the 237.5. That's the number of students that were admitted, and so the probability is this number divided by this number, which is the formula I put in here, and so that's 0.4349 or 43.49%. So part D says, suppose a student applies for early admission. What is the probability that the student will be admitted for early admission or be deferred and later admitted during a regular admissions process? So let's let F be the event that a student applies for early admission. And is deferred. So again, that's early admit, I guess applied early admit. And is deferred and later admitted. So we've got event E, which is early admitted, and event F are mutually exclusive and the addition law applies. Okay, and so that's earlier in the chapter. So we've got probability of E. See if I can find this on my screen for you here. I can insert a symbol for union here. I'll just use a space and a capital U, or maybe a little u. Union F is equal to the probability of E plus the probability of F. And we know the probability of E from here is 0.3623. So we got 0.3623. And we know from the past that the school admitted 18% of the deferred students. And we know the deferred students was 964. So the probability of F then is 0.18. Should go ahead and work that out. Equals 0.18 times 964, all divided by, and that would be the total of applications, which would be 2,851. So then the probability of E union F then is the probability of E, that's what we've got here, plus the probability of F. So we could say this plus this. So the answer is 0.4231 or 32. And that's the probability that a student will be admitted for early admission or be deferred and later admitted during the regular admission process. So the next problem I think I want to do is probably both about the same, but we'll go ahead and do problem number 5. And I can't find another one that's similar to 6, so I'll do 5. Hopefully everybody will watch this and they'll get all the points for this. So I've set up problem number 5 like it's in the book, and copied some formatting over. So all you really need are these numbers right here. And so what you'll need to do is get the total for each column. and then get the total or sum for each row. Copy that down. Just doing Control C, Control V, and then I can get a sum here, and that gives me everything. So part A asks me for a joint probability table. So the joint probability table is nothing more than taking this grand total here and dividing it into each of these numbers that are right here. So what is business full-time, engineering full-time, other full-time, and then the same for part-time. And so we can easily do that, and I want to keep my same formatting. So what I'm going to do is do a Control C, Control V, and I'm going to delete these numbers here. And what I'm going to do for this one, all it is this number divided by this number. That's going to be the same for all of them, so I'll make it absolute. So you can see the absolute up here. I just pressed F4 after I hit that value. So I hit enter, and that gives me that number. Then I can just copy this over, and I can copy these three down, and that gives me the values that I'm looking for. So the joint probabilities are these values right here. So let me do a total outline again. Okay, and then these are the marginal probabilities. So this is the answer that was given from the book. So I just wanted to show you how they got those numbers. Okay, so I'm going to go ahead and delete that. And we can go on to part B. Now, hopefully by watching this you see what I mean by show your work. You know, a lot of times I'm looking at these spreadsheets you're turning in, and people just have the numbers typed in. So I'm thinking, okay, how did they get the numbers? They didn't show any calculations. Did their friend show them this? Did they find this on the internet? You know, I need to have some understanding that you know how to arrive at these numbers and not just copy and paste them in here. So that's what I'm looking for when I say show your work. So B tells us, it says use the marginal probabilities of the undergraduate major, business, engineering, or other to comment on which undergraduate major produces the most potential MBAs. And so you can see that for business it's 38.47%. For engineering it's 27.43%. And for other it's 34.1%. So business is the undergraduate major that produces the most potential for MBA students. Now we may want to write those out so that we can use those in our calculations. So I'll do probability of B, probability of E for engineering, probability of other for other, and probability of, let's say, F for full-time enrollment. Okay. So I went ahead and answered the question in here for B as well. So let's go to, we'll scroll down, let's go to part C. And let me go back, let me move this over. So the probability of B is this. Probability of E. Probability of F. And so on. All right, now we can do C. So C asks us, if a student intends to attend class full-time in pursuit of an MBA degree, what is the probability that the student was an undergraduate engineering major? What this is asking then is, what's the probability of an engineering given that he was full-time? Okay, so if we look at our formulas, and I'm just going to paste those in for you. The formula then looks like the following. The probability of E given F, we know that to do that calculation, that's the probability of E intersection F divided by the probability of F. That's what we do when it's probability of E given something. So the given goes on the underside of the division or in the denominator. So E intersection F. All right, so here's E intersection full-time. That's from the joint probability table. That's where this 0.1510 came from. And the probability of F is 0.6130. And when we calculate that out, that's the answer we get. So if I do that here, I'll just paint this in, this formula. I want this number divided by this number. And that gives me the answer, or 24.62%. Part D says, what if a student was an undergraduate business major? So we're looking at business majors. So if we look at our joint probability table, that's going to be this one, 38.46%. What is the probability that the student intends to attend class full-time in pursuit of a MBA degree? So that's, you write that out as the probability of full-time given that they're a business major. We know that the formula then looks like this, the probability of F intersection B divided by the probability of B. So again, I think you're probably going to need to think about the wording of these problems and think about, okay, if they're mentioning something first, that is the overall probability, the bigger one is going to go in the denominator. So if we do this, F and B, the intersection of F and B from our joint probability table, so full-time in business is 0.2697. That's where that number came from. And the probability of business, that's our marginal probability here. Okay, and I can write that same formula again. And that comes out to 0.7012 if you round. So that's how we arrived at that. If we look at part E, E says, let F denote the event that a student intends to class full-time in pursuit of an MBA degree. Let B denote the event that a student was an undergraduate business major. Are events F and B independent? Justify your answer. So to use the multiplication law on page 177, we note that probability of F times the probability B should equal the probability of F intersection B. If that's true, then they're independent. If they're not true, then that's not independent. So the probability of F full-time, and the probability of business. So if we look at that, that's going to be probability of F. It's this joint probability, or this marginal probability, times probability of B, which is this value. And we see, did I use the right ones? So I check, so that's correct. So this multiplication is 0.2358 or 23.58%. The probability of F intersection B, so full time, that's this value, 0.2697. They are not the same, so the events are not independent. So I put not independent. So that's how that's calculated, and that's the logic for going through that. Another problem that I think is useful to you to work through would be problem number 9. So I put the initial table that they have there. These are the days that I believe a house has been on the market, and the cost of each house, and it's asking you for some different probabilities. And so if we look at that, we need to go ahead and create what are our totals, what are our then joint probabilities. So let me just do the sum here. Got that. And we'll need to do the sum for the rows. And we can see the grand total here is 800. So to get the joint probabilities, we'll say equals this value divided by 800 F4. Now I can copy that on down. Hold on. Copy that across. And that's our probabilities, our joint probabilities and marginal probabilities. Can copy this. And now I can answer questions. All right, so it says, what's the probability of A if it's defined as the event that a home is listed for more than 90 days being sold? Estimate the probability. So that is this probability here. So that would be the 200 divided by 800. 200 divided by 800, that's what we get here. Part B, if B is defined as the event of the initial asking price under 150, estimate the probability of B. So let me get rid of that. So that marginal probability is 100 divided by 800. So that's where this 100 comes from. And that's how we get that number. Part C, what is the probability of A intersection B? So greater than 90, under 150 would be right here. So that would be this 10 divided by 800, or this value right here. Then D is assuming that the contract was just signed to list the home with an initial asking price of less than $150,000. What is the probability that the home will take Cooper Realty more than 90 days to sell? So the way to interpret that is the probability of A given B. So what that's asking is, what's the probability of selling a house in more than 90 days, given that it's less than 150,000? And again, they mentioned 150,000 first, so that's our probability of B. So that's 0.125. We know that if we have this as our probability, we can calculate that with the intersection divided by the probability of B. That is the intersection of A and B divided by the probability of B. So here's the intersection in blue, and then here is the probability of B. When we divide that out, we get 10%. Step B says, are events A and B independent? So we've just calculated A and B. So the probability of A given B, if they're independent, would be equal to the probability of the first one, which is A. Probability of A given B is 10%. Probability of A is 25%. They're not equal. So they are not independent. The last problem that I want to go over as an example is problem number 12. It's very similar to problem 11. They both use Bayes' theorem. It's a special two-event Bayes' theorem. So it would work the same as long as you identify them correctly. So let me read what it says. We've got runningwiththedevil.com created a website to market running shoes and other running apparel. Management would like a special pop-up offer to appear for female website visitors and a different special pop-up offer to appear for male website visitors. From the sample of past website visitors, Running with the Devil's management learns that 60% of the visitors are male and 40% are female. So part A says, what's the probability that the current visitor to the website is female? And so we just look at that data that we just read, and so the probability of female is 40%. So part B says, suppose that 30% of Running with the Devil's female visitors previously visited letsrun.com, and 10% of the male customers previously visited letsrun.com. If the current visitors to Running with the Devil's website previously visited letsrun.com, what is the revised probability that the current visitor is female? And there's a second part to this, and that is, should Running with the Devil's website display the special offer that appears to female visitors or the special offer that appears to male visitors? So let's define the probability of M then is 60%. The probability of L given M, that is a visitor to the running website previously visited the Let's Run website, given that it's a female, L given F, my mistake. And the probability of L given male is 10%. So we were given this L, that is the probability of visiting the Devil website, previously visited the Let's Run website. And we want to know what is it for a female, what is it is for a male. So that's what we were given. So what we want to calculate then is the probability of female, given that it's visited the Running with the Devil website previously as a visitor to the Running with the Devil website, she previously visited the Let's Run website. So we use that formula that's given to us in the book, the probability of F times the probability of L given F. We have that information divided by the probability of F times the probability of L given F plus the probability of M times the probability of L given M. See the pattern here? So this is the same, but now we have to put in the male probability of that. So that's 60% times that 10%. That was the 30% times that's the total that previously visited. When we divide that in just for the females, we get this. So the revised probability that the current visitor is female is 66.67%. So to answer the second part of the question is then Running with the Devil website or company should display the special offer that appeals to female visitors, because it's more likely that this visitor is a female, 66.67%. And hopefully that will help clear up some confusion and help you do well or do better on those problems. That's all I have to say for that.